Hey everyone, today we are going to look at some level 3 thermochemistry, focusing on the 2018 examination paper. So let's start with the question 1 today. And before we start, smash the like button, subscribe if you haven't. It will really help the channel grow. As you can see, I'm pushing a lot of videos just before the exams. Because this is where a lot of people will just come on for last minute help, and if you can spread the message, share the channel with your friends, that will really help them and really help me to grow the channel as well. Okay, so let's get into question 1. So question 1 is a type of question looking at the electron configuration. So the first thing I tend to do is just look on the periodic table and figure out how many what is the atomic number for the elements. So for vanadium is 23, for copper is 29, for bromine is 35. And then what you can do is just arrange them, make sure they add up to the number of electrons, and then just be careful with these charges. Okay, so let's look at vanadium first. So 23 electrons, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 4s2, 3d3, and that will give you 23 electrons. So that's, if you add up these numbers on the top right hand side, they should equal to 23. Now for copper, I would like you to do it this way. Do the atoms first, do the element first rather than the ion, because if you went straight to do the ion, then you're most likely gonna get this wrong. Okay, I know it's only a cheap question, but you might, like I explained in the 2019 video, being able to do the electron configuration will be very beneficial if you were to do atomic radius, ionic radius, just help you to gain a better understanding of the concept. Okay, so for copper, if I'm doing the copper atom, 29 electrons. So remember for year 13, the copper and chromium a little bit different. So once we get to the 3p6 stage, we have 4s1 3d10 instead of 4s2 3d9. Okay, so this is more correct. Now what does the plus sign mean? Plus means we remove a electron, so we remove 4s before 3d, so it's going to look like 1s2, 2s2, 2p6, 3s2, 3p6, and 3d10. Okay, now for Br minus, you can, it's normally the positive ions that you have to watch out. I normally do it this way, do the atoms first and do the ions. But if it's a negative ion, you normally have 35, now you need 36. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. That's 2 plus 2 plus 6, that's 10, that's another 10, that's 30. I need 6 more, so it goes to 4p6. Okay, very straightforward. Next one, explain the factors influencing the trends in first ionization energy and the atomic radius across the second period of the periodic table. In your answer, you should describe trends in both explain the factors, and then relate the trend in ionization and trend in atomic radius. Okay, so when you are looking at these type of questions, this is more generic, so you're not referring to any elements, like any atoms versus, or any element versus another element. But just remember, if you have a periodic table in front of you, as you go across the periodic table, the atomic radius, so the radius decreases, and then as you go down the atomic radius, as you go down the period, as you go down the group, the radius increases. Okay, so that's your trends. So if you just memorize these, you get achieved. And then the ionization, the first ionization energy is the opposite. This one would increase, and this one would decrease. Now, why does it do that? So the factors that we're interested in, the first one they always want you to consider is the number of protons. Because as you go across the periodic table, you have more protons, you have more electrons. But because you have more protons, this means you have a stronger nuclear charge because you have more protons. I mean, that's pretty straightforward, I hope, or a strong charge, right? stronger nuclear charge, or you can say it is the a stronger force of attraction coming from the nucleus, which is a nuclear charge. Okay, and the number of protons is one key thing, because the more protons you have, the stronger force of attraction you have. Okay, the stronger force of attraction you have, then the valence electrons would experience more force of attraction, and they'll be closer to the nucleus. Hence, the radius will be smaller. So this is one thing you need to consider. Okay, the other factor that you need to consider is the location of the valence electron. Okay, so this is the shielding effect. Okay, so these are the two factors that you need to consider. So when they say explain the factors influencing the trend, these are the two things that we are looking at. Okay, so I'm just going to verbally explain this because we have a lot of answers underneath. Okay, so just let's see if this makes sense. All right, so as we're going across the periodic table, let's say if I go from, doesn't matter what period, they said the second period, it doesn't really matter. As you go across a period, the number of protons increases because the atomic number increases. So that means the number of proton increases, and therefore you have a stronger nuclear charge. Okay, so we have the top bullet point, and that's increasing. And then what about the shielding effect? Well, as you go across the same period, the element over here, which is lithium, has electron arrangement of 2-1. We're not yet 12s anymore. We do 1s2, 2s1. And if you go to this side, it will be like say 2-7, which is your floor ring, 1s2, 2s2, 2p5. Okay, so this is your lithium on the left hand side, this is your fluorine on the right hand side. As you can see, yes, I have more electrons. This is 9 electrons altogether, this is 3 electrons altogether. But then if you look at the energy level, the electrons are being added in the same energy level. The valence electrons are both in the second energy level. So you are kind of adding electrons. This is the example I normally use. It's not really correct because we're not looking at the three-dimensional side of things. But if I just think of your science room, think of your chemistry classroom, if the teacher is standing in the front, let's say where I'm normally standing, and then in the first row, the second row, the third row, let's say if I'm standing in the middle of the class at the very front, just in front of the whiteboard, and then I'm putting students in the second row, so like just across the classroom, just adding them across the row, and that's essentially what I'm doing to this particular trend. I'm adding students in the same row, and the distance between them and myself will be relatively the same because the shielding effect between me and these students will be the same, which is the students in the first row. So they would have a similar sort of shielding effect, but because I have the center, like say the teacher gets bigger because there are more protons as the atomic number increases, the nuclear charge is now greater, and there's similar shielding effect, and as a result, the atomic radius would increase, because the valence electrons would experience a stronger effective nuclear charge because they're being added in with because of the similar sort of shielding effect. Therefore, they would experience more sort of attraction, and they will be attracted closer to the nucleus, and that's what determines radius. And ionization energy is completely the opposite, because what is ionization energy? It's the same concept. Once you understand radius, you need to understand radius to understand ionization energy. Because the atoms are getting smaller and smaller as we go across the period, that means it will be harder and harder to remove a valence electron from the atom. Because what's first ionization energy? First ionization energy is the amount of energy required to remove 1 mole, to remove 1 electron from 1 mole of gaseous atom. So if these electrons are really strongly attracted by the nucleus, then it will be really difficult to remove these electrons away, to break this interaction. So as the radius decreases, as the radius decreases, the ionization energy increases because it gets harder and harder to pull them away, to remove electron, and vice versa. The radius increases as you go down. So if we think about going down the group, so we have, yes, there's a stronger nuclear charge as always, stronger nuclear charge, because if you compare, let's say, again, if I use lithium over here has 3 protons, and then if I compare sodium, which has 11 protons, obviously the 11 protons is a stronger nuclear charge compared to the 3 protons because they have more protons. Okay, but in this case the shielding effect is more significant, because despite having a stronger nuclear charge in sodium, with more protons, the valence electron of sodium is in a higher energy level. So for lithium is 1s1 1s2 2s1, the other way around, 2s1, and then for sodium is 1s2 2s2 2p6 3s1. So I mean, the third energy level is much further away, because that valence electron would experience more shielding effect from all of these inner shells of electrons. Okay, so in this case the shielding effect is more significant, and that will result in the radius being bigger because the valence electrons will be further away. Okay, and then the ionization energy will be the opposite. Okay, so I think that's I think I broke it out really thoroughly. I normally wouldn't spend this much time on a particular question, but this is a really, it comes up every single year, so it's pays, it makes sense to spend a lot of time on it. So as you can see, first ionization increases because there's an increase in number of protons, therefore more more nuclear charge, and this is an important phrase: electrons are added in the same energy level, there's no actual shielding. Okay, so so this just means, I'm just going to add that, this just means no extra shielding. So the valence electrons are experiencing the same amount of shielding effect. Okay, now the electron increases, therefore more energy is required to remove them, and the atomic radius. I normally, it's really weird with how the answers are structured. I would write the radius first. So the radius decreases because there's more protons, strong nuclear effective charge added to the energy level. So you have a stronger pull on the valence electron to the nucleus. Okay, so as the energy decreases, this is the same factor for decreased nuclear charge and more protons. So this is going across a period. So yeah, so this is the same thing. All right, so very straightforward. I do hope. I mean, if you still confused, rewind, listen to the explanation again. Okay, now let's do the next one. Lewis diagram. This is more of my preferred stuff to teach, because I just enjoy doing Lewis diagram a little bit more. So first thing first, find these elements on the periodic table. So if you look for AS is 33, has atomic number 33. AS has 5 valence electrons, it's in group 15. Fluorine has 7 valence electrons, it's in group 17. So if we count the number of valence electrons, it will be 5 plus 7 times 5, because there are 5 fluorines. So it's just 5 times 8, which is 40 electrons. So your diagram need to have 40 electrons. And BR F5, BR is 7, and then the fluorine is again 7, so 7 plus 7 times 5, which is 42 electrons. For this one you need to have 42 electrons. This one you need to have 40 electrons. So let's draw them. So once you have done that, the way of drawing these diagrams compared to how you do in level 2 is it's much different. I actually think it's a lot easier, because if you look at all of the elements that we give you are like always chlorines and fluorines and hydrogens. They're always single bond, they don't double bond. So if you have AS at 5, so just put the 5 fluorines around and then just worry about the fluorines first, because you have an extended octet, and make sure every one of these fluorines have 8 electrons around them. Oh man, here it comes again. OneNote is trying to be a smart ass and trying to connect all my dots where I don't want them to connect my dots. Don't do it. This is the first world problem when the computer program is trying to be really helpful, but it's not being helpful. Okay, so once I've done that, can you see that's 8 electrons, that's 8 electrons, that's 8 electrons, that's 8 electrons, and that's 8 electrons. 5 8 is 40, and I've done my loose diagram. Okay, now if I do BR F5 is going to be slightly different. So same thing. If I do, now you can arrange these however you want, doesn't need to look the same way as I did. So same method, single bond everything. Don't worry about what goes in the middle first, just do the side first. You see those two lines, you don't draw this as a line. I mean, some of you are gonna come back and say, you teach me how to do this using lines, and then you get marked wrong. Like, no, that's just OneNote being stupid. All right, there we go. So if you count that, I mean, we just did it. All of those will be 8 electrons. I need 42. I'll only have 40. And this is why the bromine has a lone pair of electrons above it. This is why ASF5 is trigonal bipyramidal or bipyramid. Why? Because you have 5 regions of the electron density, and they're all connected. And for BRF5, this is actually going to be square pyramid. And why is that? Because this has I'm just going to put this in bracket, don't write this down, but I want you to understand this has an octahedral arrangement. Okay, so because you have 6, so this is 1, 2, 3, 4, 5, 6 regions electron density, but you can't see the lone pair, hence it's a square pyramid. It's almost like you have a square piece of paper, and then you have something that's on top of it and something that's underneath it, but then you can't see the side, you can't see the bit underneath the square plane. So you have a square base, and if you connect all the dots between the square base and the point above it, that looks like a pyramid. So it's a square pyramid. All right, next one, XCF4. So explain if this is polar or non-polar. This is actually non-polar. And this is actually a really good example. Can you guys see these lone pair of electrons around XE there? The only year 12 and 13 molecules that will be non-polar that have lone pairs of electron is a square planar shape. Anything else have got lone pairs of electrons around the central atom are polar. Think of bent. Think of this one that we just did. Think of square pyramid. Think of what's the other one? Seesaw, T-shaped. All of those have lone pairs of electrons around the central atom. All of them are polar. It is only square planar that is non-polar. Okay, assuming that you're bonding to the same atoms. But just for a really easy trick for you to remember, just remember. All right, if I draw a loose diagram, I see lone pair of electron in the middle. Okay, so if it's not square planar, it's polar. That's just for you to get some easy points. Okay, now how do we explain the shape? So the shape for XCF4, let's just count. So that's 6 regions. I'm not going to write all this, so just hear me out. 6 regions of electron density around the central atom. You got 4 of them that are connected. You got 2 lone pairs. So these regions of electron density will position themselves as far away as possible to minimize repulsion. Therefore, you have an octahedral arrangement. You have an octahedral arrangement, but then you are going to see a square planar shape because you do not see these two lone pairs electrons. Okay, now the polarity, you need to talk about Xe and F. This bond is polar. Why is that polar? Because of the significant electronegativity difference between the two elements, between the two atoms. So the bond is polar, and that will result in bond dipoles. But if you actually look at it's the square planar shape, if we come back to here, the square planar shape is actually symmetrical. So what that means is that the bond dipoles are arranged symmetrically, and they cancel each other out, and then they spread the charge evenly, and therefore the molecule is non-polar. So let's just highlight some of these here. I think it's pretty much everything I talked about. Let's say 6 regions, 4 bonding, 2 non-bonding. They arrange as far as possible, minimize to give you the octahedral arrangement. That's not the final shape. Because of lone pairs, you can't see them. It's a square planar shape. And due to the significant electronegativity difference between the atoms, you have polar covalent bonds and you have bond dipoles. Okay, so you create bond dipoles, and because the shape is symmetrical, you have got a non-polar molecule every single year, guys. Just study it. Always talk about the bond first. Talk about the bond, talk about the significant electronegativity difference, talk about the formation of polar bonds, talk about bond dipoles. And once you've done that, talk about the symmetry. Is it symmetrical? Is it not symmetrical? If it's symmetrical, then your bond dipoles will cancel out. If it's not, then they don't cancel out. Okay, so I do hope this video is a little bit longer than usual, but that's why I've been putting off 3.4, because it's the longest one to explain things. But once you get the hang of it, it should be pretty straightforward. Okay, as always, I'll move on to question 2. Hope you guys enjoyed the video, and I'll see you guys next time.